we have the transformer, and we have been representing this transformer in this fashion. That is, we draw a square core, and then we have the windings, which are written like that. This is the primary and this is the secondary. This is N1 number of turns, this is N2 number of turns, NP number of turns or NS number of turns depending upon. Now we shall represent this as an electrical symbol. We have an electrical symbol associated with this, which will be used in all the circuit diagrams. That is, it is written in this form. There are two coils like that, and then there are two parallel lines which are drawn in between to show that these two are coupled with a core inside in between. This is the primary or E1, this is the secondary or E2, there is a primary current or I1, secondary current or I2. This is the, and there is a N1 is to N2, number of turns in the primary, number of turns in the secondary. This is how a transformer is represented as a component in an electrical circuit. Now here we have less number of turns here and more number of turns on the secondary side. This would in general imply that the primary voltage is smaller and the secondary voltage is larger, and it is a step up transformer. That would be a step up transformer. If the symbol is written in this fashion, as shown here, with the primary voltage more than the secondary voltage, and consequently the primary number of turns being more than the secondary number of turns. Now here you have N1 less than N2, and here you have N1 greater than N2. So which means E2, the secondary voltage, is less than the primary voltage, and such a transformer is called a step down transformer. Step down transformer. And if one writes symbol with equal number of turns as shown here, then such a transformer is a 1:1 transformer. This is the primary E1, this is the secondary E2, the primary current I1, secondary current I2. This is a 1:1 transformer. The secondary voltage E2 is the same as the secondary current, primary voltage E1. The main function here is that galvanically the primary portion of the circuit and the secondary portion of the circuit are isolated, meaning there is absolutely no contact between the primary portion of the circuit and the secondary portion of the circuit. For such applications where one uses a transformer just for the purpose of isolation, galvanic isolation between one part of the circuit and another part of the circuit, then such a transformer is called a isolation transformer. Of course, a transformer can be used to perform more than one of these functions, like it could be used for performing isolation plus step up, isolation plus step down, so on and so forth. Now, to complete the symbolic representation of the transformer in the electric circuits, there is one more item that we need to add, and that is we have the primary winding, secondary winding. They have two terminals here, we have two terminals here. Let us say this is E1 and this is E2, and we have a core in between. This is N1 is to N2. We also add a dot. So, this dot indicates that at the dot end the polarities on the two sides of the transformer, that the primary side and the secondary side, are in phase. That is, if the voltage is measured at this point with respect to the non-dot terminal, and likewise on the secondary side the voltage measured at the dotted terminal with respect to the non-dotted terminal, the voltages will be in phase. We have a transformer this fashion, and let me put the dots like this, and let us call this terminal as A and this terminal as B, this terminal as C and this terminal as D. Now, we are going to apply, let us say, some voltage across the terminal VAB. We now apply a voltage across the terminal VAB. It is an AC voltage. Now, how does the waveforms look across the primary and the secondary with respect to time? Let us say VAB, meaning we are measuring at A with respect to B, and the other one is VCD, we are measuring at C with respect to D. And so, if we had a waveform of this sort across VAB, which is applied, then the voltage VCD will be in phase, as shown. Now, if we have a dot polarity of this fashion, which depends upon the winding sense. So, instead of winding the secondary, let us say, which was clockwise in the previous case, it now becomes anti-clockwise. The dot polarity is now in this form. So, therefore, the secondary is no longer, VCD is no longer like the case that we saw before. It is now so when A is positive with respect to B, it means that the dot portion will be positive with respect to the non-dot portion. So, if A is positive with respect to B, D will be positive with respect to C. So, in VCD, C will be negative with respect to D. So, we would see that there is a reversal of polarity. And when A is going negative with respect to B, D is also going negative with respect to C, but C, if D goes negative with respect to C, C goes positive with respect to D, and that is what is happening. CD is positive during this time. So, you see that there is a 180 degrees phase reversal. So, dot polarities are crucial to indicate the phase relationship between the primary and the secondary. So, the phase relationship between the primary and the secondary are represented by the dots, called the dot polarity. So, the dotted portions are supposed to be in phase. And now, these dot polarities can also be used for generating the phasor relationship to get the phasor diagram between the various parts of the circuit, including the transformer. Let us draw the phasor relationship between the primaries and the secondary for any given dot polarity. So, let us have a primary coil, let us have a secondary coil, there is a core, and there is a primary. We will keep it as E1, consistent with the other. There is a primary voltage E1 and there is a secondary voltage E2. As of now, there is no load connected here. So, let us now do that job of connecting a load across the secondary. This means there is going to be a current I1, there is going to be a current I2 in the secondary, and this is N1 is to N2. Now, let us also have the dot polarities like that. So, which means when the dot side is positive, the dot side here is also positive. Note that here when the dot side is positive on the primary side, this is the secondary, the current is entering the dot, and here the current is leaving the dot. When the current is entering the dot and this is positive, energy is put into the transformer. The dot side is positive, current is leaving the dot, energy is removed from the transformer. So, that is how the energy passes through the transformer, goes from the primary to the secondary side. Now let us represent this as our conventional winding that we used to do before with a rectangular core. Let us say we have a core as shown here. There are some windings. So we have the primary side winding. We also have the secondary side winding. We are going to connect a source, an AC source of frequency F across the primary, which is going to result in voltage E1. So the applied and the induced are going to balance each other, and there is going to be a load resistance or an impedance here, which is going to result in E2. Let's say that I mark the generated voltage and let me call that one as EG. Under normal conditions, EG will be same as E1. Now let us say there is an I1 and now there is an I2 flowing through the load. This has N1 number of turns and this has N2 number of turns. Okay. So this current I1 flowing through N1, initially when the load was not there, let us say initially load was not there, this is open, which means I2 is 0. So the current flowing through N1 generates a flux due to the ampere turns Ni. And let us say this is N1 I1. Now if the load is connected and this flux N1 I1 which is generated in the primary is linking the secondary and multiplied by N2, a voltage E2 is generated by the Faraday's law of electromagnetism. And the moment you connect the load here, E2 divided by whatever the impedance Z2 is going to result in a current flowing through the secondary circuit. Now this current is flowing through this coil, which is going to provide a cancelling motive force. So MMF is provided here, plus minus, let us say here at a given instant. Now a current flowing out of the dot, isn't it? Let me put the dot. The current is entering the dot, current is flowing out of the dot, is going to create a cancelling MMF. So what happens? We are going to have an MMF which will cancel the earlier MMF, and this is N2 I2. And due to the cancelling effect, the MMF is reduced. A reduction in the MMF means on this side the induced EMF E1 has reduced, but the applied voltage EG is still the same. The EMF here E1 instead of being same as EG has now reduced, which means there is a voltage potential difference which will cause a very high current to flow. So the current will keep on increasing till the current I here goes back, balances the cancellation due to this. So the current I1 here will increase till N1 I1 balances the cancellation due to I2, N2 I2 that occurred due to the presence of the load. So, which means I1 would have increased such that E1 now matches EG. So, this would mean that there is a cancelling MMF provided by the primary N1 I1 dash such that this is cancelled out. And what will remain would be N1 I1 under the case when there was no load, and that would be the magnetizing component of the flux. So, the flux in the core is going to be same as it was under no load condition. Whatever may be the load you may increase, there will always be a cancelling ampere turns that gets generated in the primary, which will cancel out the load induced ampere turns, and thereby the flux in the core is always going to be constant whether it is no load or loaded condition, such that the volt circuit balance is maintained according to the previous equations that we saw, which will make the transformer to operate in the magnetic zone. Now, with this concept, now we should be able to draw the phasor diagram. So, we have here the primary, and the primary is connected to a source, voltage source. I will still name it as EG as the generated voltage or the applied voltage. This is the generator voltage which is applied, and there is a induced voltage across the primary. Effectively E1 equals EG always at every instant of time. However, to distinguish between the generator voltage and the induced EMF or the induced voltage, let us have this distinction. And we have a core and then the secondary, and the secondary is connected to a load, and the load could be resistive or RL or RC or RLC, any impedance Z2. Now, there is a voltage across the secondary and we call that as E2. Now, the current through the primary we will call it as I1, current through the secondary we will call it as I2. We have the dot polarities as shown here, and this is N1 is to N2. This will complete the way the transformer looks. Now, let us draw the phasor diagram for this transformer circuit. This is the spatial coordinate systems, as I have been saying. We have seen quite a few times in the earlier classes or earlier sessions while discussing the phasor diagrams with sinusoids. This is the alpha axis and this is the beta axis. So, we need to choose some reference phasor along this direction, and remember that phasor means same as the vectors, except that the amplitudes are effective values or the RMS values. Now, we shall choose the input voltage as the reference direction, that is, this would be the EG direction that we are choosing. Now, as EG and E1 are one and the same, this also means that we have E1. in phase with Eg. Now by the dot polarities, let us say N2 is, for the moment, N2 is less than N1, which means it's a step down. E2 is less than E1. From the dot polarities, we say that E2 and E1 are in phase, exactly, they follow each other by the dot polarities, which means E2 is in phase with E1. Now let us say that Z2 is a lagging power factor load, that is an inductive load, which means I2 has to lag E2. So let us have I2 lagging E2 by some angle theta. What happens to I1? Now we see that N2 is less than N1. We know that E2 by E1 equals N2 by N1. So E2 is N2 by N1 into E1, which is less than E1, and I1 by I2 equals N2 by N1. This is the inverse proportionality. So N2 by N1 is less into I2, sorry, this is, yeah, N2 by N1 is also equal to I1 by I2. So N2 by N1 is less, and therefore I1 will be less than I2, whatever the value of I2. So I1 will be less than I2 in this case. E2 will be less than E1 in this case. So which means we will have I1 here, because by dot polarity I1 and I2 will be in phase, because E1 and E2 are in phase. So I1 will have a vector in phase with I2. Now what about the flux in the core? So the flux in the core will be lagging the voltage by 90 degrees. This is the flux phi m in the core. This is because we have V which is equal to N d phi by dt. There is a d phi coming, which is N j phi m. So we see that the voltage vector is whatever the phi m vector direction rotated by 90 degrees because of the j, and that's what it is. That's what it means by this j operator. So phi m should lag voltage by 90 degrees. That's what it means. So this would be the vector diagram of an ideal transformer.